Welcome back to the series of talks in physics of solids. In the last session, we were discussing about the electrical conduction. There we talked about the huge range, the 24 orders of magnitude in the range of conductivity values which the materials are having. So, they do range from NDFE, which is from 10 raised to minus 20 minus 18, 10 raised to minus 8 to 10 raised to 16 for the silver. So, any model which tries to explain the electronic conduction should be able to account for all those materials. And not only that, you do have different classes of conductors. You know the names by yourself, metals, semiconductors, semi-metals, insulators and so on. So, here the free electron model, the classical and the quantum free electron models were able to explain the metals to some extent, to a greater extent I should say, but they were not able to really explain the conducting phenomenon in metals, semi-metals and semiconductors. So, people started thinking about newer models, and one of the model which is a prominent one is what we call as the nearly free electron model. As we discussed in the last session, it was really a problematic to assume that, or it is not really logical to assume that the electrons were travelling as free particles, not at all having any interaction with each other or with the lattice. But the nearly free electron model really tries to modify all those concepts. Here in the nearly free electron model tries to model the band electrons, and they are treated as perturbed only weakly by a periodic potential of the ion cores. So, there is a ion core potential, and the conduction is being perturbed by the conducting electrons are really being perturbed by the presence of these periodic potentials. There is a famous quote by Bloch in this regard, who really proposed this or who really embarked into this concept of periodic modulation. So, let me read out his quote, which tells that when I started to think about it, I felt that the main problem was to explain how the electrons could sneak by all the ions in a metal. By straight Fourier analysis, I found to my delight that the wave differed from the plane wave of free electrons only by a periodic modulation, unquote. So, this was a famous quote by Felix Bloch, who later proposed the Bloch theorem. So, Bloch theorem really forms the foundation stone on which the nearly free electron model is being based. So, what is the model telling? So, here in the free electron model, we were assuming a wave equation. In the quantum free electron model, we were indeed assuming a solution psi is equal to e raised to I k x. But in the Bloch's theorem, he introduced a new term which really takes into account the periodicity. So, what is the periodicity about? This is the periodicity which the electron will see during its travel from one end of the crystal to the other. So, these are the so called lattice points or the atoms present in the lattice. So, it gets modified as psi is equal to e raised to I k x into u k x. So, it is the u k x is the factor which accounts for the periodicity. Let us see further into the so called Bloch functions. Now, consider an electron moving in a periodic potential, say we denote it by V x. The period of the potential is A. As I told you, A is the distance between two different two nearby lattice points, right. What will be the Schrodinger equation for this periodic potential? Now we are in a situation where you are assuming a periodic, you are assuming a potential also. So, in that case the Schrodinger equation will get modified as minus of h cut squared by 2m into d squared psi by dx squared plus Vx into psi equal to E psi, simple Schrodinger equation, right. So, quantum mechanically the electron moves as a wave through the potential. Due to diffraction of these waves, there are bands of energies where electron is allowed to propagate through the potential, and the bands of energies where no propagating solutions are possible. It is just because of the presence of this potential. The Bloch's theorem states that the propagating states will have the form psi is equal to e raised to I kx u kx, and as I told you, u kx is a periodic function with a periodicity a. So, and that is what we call as the Bloch theorem, and the one electron wave function in a Bloch theorem is what we call as the Bloch function. Okay. So, we have the Bloch theorem and the Bloch function. Bloch theorem is psi is equal to e raised to I kx u kx. But a particle in a periodic potential must have the form of Bloch equation such that the translation operators will commute with the Hamiltonian. So, in the beginning we assumed a periodic potential u k r, and if we assume that there is a translation vector t, so u r is equal to u of r plus t, and if I expand the t value, u of r plus u1 a1 plus u2 a2 plus u3 a3 and etc. So, what will be the modification that will bring into the psi k? Psi k of r plus t is equal to u k of r plus t into exponential I k of r plus t. So, there you can write it as u k, but you already know that u r is equal to u of r plus t, right, because that is the periodicity which you have imagined in the which you are assumed in the beginning of our derivation. So, therefore, u k of r plus t I will write it as u k r, and the exponential I k dot r into exponential I k dot t, but on combination of u k r into exponential I k dot r is equal to psi k r. Therefore, psi k of r plus t is equal to psi k r into exponential I k dot t. So, what is the significance of that finding? With the assumption that there is a Bragg reflection, you know what is Bragg reflection already from our earlier sessions, I assume that. So, with the assumption of a Bragg reflection, one can plot the allowed energy states with one single parabola, right. But here, because of the periodicity psi k of r plus t is equal to psi k of r into exponential I k dot t, because of the periodicity, now one cannot plot the single parabola. Instead, one has to plot multiple parabola at what distance with each other? You know the answer, which is actually the reciprocal lattice vector, because it is a Bragg reflection. So, you need to plot different parabolas at an interval g, which is the reciprocal lattice vector, and these multiple parabolas will start crossing each other at certain points, right. So, now at those crossing points you will have certain gaps. That is how you explain the origin of band gap in a typical semiconductor, because in a semiconductor you have a band gap, whereas in a metal you do not have a band gap. The free electron model was not able to explain the band gap of the semiconductors, but here with the nearly free electron model and the Bloch's theorem, one is able to explain the band gap. So, how do you pursue that? So, now you have two parabolas, right. One is moving to the right side, for example, and another is moving to the left side. So, these two points do crossover at certain points. So, what will be the effective wave function at those points? So, now since there is a right arm parabola and there is a left arm parabola, left arm of the parabola which meets each other, you can imagine there is a psi plus and a psi minus term. So, in the psi plus term you have exponential I pi x by a plus e raised to exponential minus of I pi x by a. So, that will be 2 cos pi x by a. And what will be the psi minus? Psi minus will be exponential I pi x by a minus exponential minus I pi x by a, which will give to be 2 I sin pi x by a. So, now if I take the probability, how to take the probability? In the quantum mechanics, normally you will square it, square the wave function, right. That is, after all, that is one of the big significance of the wave function in the concept within the quantum mechanics. So, we square the wave function psi squared, psi plus squared and psi minus squared, which I call the probabilities by the name rho plus and rho minus. So, that will come to be cos squared pi x by a and sin squared pi x by a. What does that mean by? Now, this means that a plane wave which is having the same probability at all points, but here we have a situation where of psi plus and psi minus giving to a rho plus and rho minus probabilities, right. So, the psi plus will favor the piling of electronic charges exactly above the ion core. The exactly opposite situation will be for the psi minus. So, what does it mean by? Which means that you will see a gap between the psi plus and the psi minus crossover regions, and therefore the band gaps. So, at the same k value you have the eigen values of psi plus and psi minus differ, and this implies that the energy dispersion curve, which is continuous throughout a zone, shows a gap with unequal roots at the zone boundaries, and this really explains the origin of band gaps. So, the nearly free electron model was really being able to explain the origin of free electron model. So, that was it. Now, in our free electron models, we have assumed the potential wells, right, the one dimensional, 3 dimensional potential wells, but the real picture is quite different. Like we started assuming in the case of nearly free electron model, there are different regions for the same lattice, where a electron, a travelling electron will see the periodicity. So, really saying the analysis of a realistic periodic potential would be very complex. It may not be really having a you can draw 100 images, but even 100 images may not really approximate the real situation, which will be different from sample to sample or from material to material. But here we need certain kind of simplifications. In that context, the Crony-Penny model gains a lot of importance. So, what is the Crony-Penny model? The Crony-Penny model basically tried to model the motion of an electron through a one dimensional periodic potential. Here the electron motion is considered across a one dimensional array of square potential barriers. So, you have a different the square shaped potential barriers, which the electron will see during its travel from one end to the other end of the so called conductor. And this picture you must have already seen when you have when you have discussed the about the quantum in the introduction to quantum mechanics, where you have assumed different barriers at different points, barriers having width a, and the potential barrier was having width b, and so on and so forth. So, we will do something similar here. So, here the electron motion is considered across one dimensional array of square potential barriers of width a, which is separated by potential barriers V0 having width b. And in other words, the Vx in Schrodinger equation is a periodic square wave in the Crony-Penny model. It looks like the image you can see there. A virtue of this model is that it is possible to analytically determine the energy eigenstates and eigenfunctions. It is also possible to find analytic expressions for the dispersion relation E versus k and the electron density of states. Now, we have two distinct regions, right, which is one is the well region and another is the barrier region. And from your quantum mechanics classes, you know that the solution of these of the Schrodinger equation in both these regions are different. So, what are they? The equations are d squared psi by dx squared plus 2m by h cut squared into E psi equal to 0 in the potential well region, which is from 0 to x lies from 0 to a, like in the picture you see there. Now, in the second region, which lies from minus b to 0, which is actually the potential barrier region, the Schrodinger equation will correspondingly get modified as d squared psi by dx squared plus 2m by h cut squared into E minus V0 psi equal to 0. A simultaneous solution of the above equation we need to find out in terms of the periodic Bloch function, and that can be represented by psi x is equal to ux into exponential I k x. So, solving the above equations, which is actually what is that equation about? That is for the in two regions. We have the Schrodinger equation in two different regions. One is in the well region and another in the barrier region, and we assumed a solution based on the Bloch function. And if we apply that, so apply that and solve the equation, one will reach an expression p sine of alpha a divided by alpha a plus cos of alpha a is equal to cos k a. One can easily find out this solution. So, the best book would be to Kittel. Kittel does describe the simple steps with which one can reach into that expression. So, p of sine alpha a by alpha a plus cos alpha is equal to cos k a, where alpha is equal to root of 2 m e by h cut and p is equal to m e v 0 b a by h cut squared. Let me assume that you understood all the quantities there. M is the mass of the electron, V 0 is the potential, B is the width of the potential barrier, A is the width of the well, and E is the electric potential which you have applied. So, there are only two variables in the above equation, namely alpha and the k, and the right hand side of the equation is bounded, since it can only assume the values between plus 1 and minus 1. The cos term there, it can only assume the values from plus 1 to minus 1. Now, what will we do? We will try to plot this equation, right. The p of sine alpha a by alpha a plus cos alpha a is equal to cos k with respect to in the x axis we will take the alpha values. So, now if we plot that equation, you will find that since there is this kind of a boundary problem that it can assume only the values from plus 1 to minus 1, as I have shown the image there, only those values can be taken which lies between plus 1 and minus 1. which means that only the shaded portions in that image can be taken as valid solutions. So, what is the implication of that? That image will lead into a picture as shown there, where we have the band gaps. All through we will have band gaps in those regions which lies outside the region of +1 to -1 for the right hand side. So, therefore, we have a system where the band gap is existing. Now, we have the band gap. So, now let me quickly go through quickly touch upon the concept of the semiconductors. So, whenever the picture of band gaps comes into picture, we invoke the concept of semiconductors. So, there are basically two types of semiconductors. One is the intrinsic semiconductor and it is the extrinsic semiconductor. And you have the concept called the band edge, where band edge means it is the topmost level of the valence band and the bottommost part of the conduction band. In between you have what you call as the band gap, right. And the intrinsic conductivity. So, what is the difference between intrinsic semiconductor and extrinsic semiconductor? Intrinsic semiconductor is semiconducting by itself in its nature, whereas the extrinsic semiconductor is made to be a semiconductor with the appropriate doping. So, the intrinsic conductivity and the intrinsic carrier concentrations are largely controlled by a ratio, which is the ratio between the band gap of the material and the energy offered by the temperature, which is kBT. So, Eg by kBT. Now, if you take two different semiconductors, right, in that case even the intrinsic electron concentration would be totally different. Why? It is because of the presence of band gap. So, as you can see in the image there, I have shown there two graphs side by side. One is of that of the germanium and another is that of the silicon. And if you look closely into the x axis of that graphs, the temperature ranges in which these kind of phenomena do happen, in which the electronic concentration for similar electronic concentrations for germanium and silicon, the different temperature ranges are involved. Why that is happening? Because of their difference in band gap. The germanium is having a band gap of 0.66 electron volt and silicon will have of something like 1.1 electron volt. So, that difference really contributes or gets reflected in the intrinsic carrier concentration. And when it comes to semiconductor, there is one very important concept there, which is related to the band gap, of course. There are two types of semiconductors. One is the direct semiconductor and direct band gap semiconductors, another is the indirect band gap semiconductors. So, what is the difference between them? We have already discussed about the reciprocal lattices and the associated k values. So, it ranges from -pi by 2a to +pi by 2a, right. So, and you have the conduction band and the valence band getting originated. If the lowest point of the conduction band occurs at the same value of k of the wave vector as the highest point for the valence band, then we call them as the direct band gap materials. So, as you can see the image there, say for example, in the gallium nitride or cadmium sulphide, you have the situation where there is no need of a phonon, it is just photon, it is just about the photon. You have the lowest point of the conduction band and the highest point of the valence band at the same point. So, the conduction is bit more easier. So, that is that kind of situation is suggesting you a direct band gap semiconductors. And now, what is the indirect band gap semiconductor? You can guess yourself, where the lowest point and the highest point does differ by a delta k value. So, who will cover that kind of a gap? It will be covered with the help of phonon, right. So, in the case of a indirect band gap semiconductor, you will have two parties involved, one is the photon and the phonon. So, if we take into consideration say an optical absorption experiment, as I have shown in the image there, for pure indium antimonide, right, it is a very important compound in the semiconductor world. You will have a sharp edge in the conduction regime, because the band edge is really well defined. You have a direct semiconductor. Whereas, in the case of an indirect semiconductor, if I take the absorption versus the photon energy, I will see a small beak there, like the one which you can see in the image there. So, the conduction will begin at a slightly at a earlier point than the real conduction is starting. So, that is what. Now, what are the particles which are responsible for conduction in a semiconductor? They are the electrons and the holes. So, the vacant orbitals in a band are called the holes. The holes act in an electric field and magnetic field as if it is an electron with charge plus E. So, that is why we always consider holes to be exactly opposite as that of the electrons. So, there are certain 5 characteristics of the holes which is well explained in Kittel. Let me just slightly touch upon, I am not going to explain any of them. One is that the wave vector kh is equal to minus of ke. Second property, the energy of the hole is equal to minus of the energy of the electron, and the hole velocity is equivalent to electron velocity. The fourth property, the mass of the hole is equal to, the effective mass of the hole is equal to minus of the effective mass of the electron. And the fifth property is h cut dk by the equation of motion for hole is that of a particle of positive charge electron, which is actually, which means that it comes from the equation of motion. You can read those things in detail in the Kittel to people who are interested in exploring them more. So, let me touch upon another important concept here, which is called the effective mass. So, what is effective mass? Without explaining that, the electron effective mass is actually giving you is predicting the curvature of an electron band. So, the electron effective mass is inversely proportional to the curvature of an electron band. This implies that the carrier effective mass can be determined from the electronic band structure or the EK relationships. So, the effective mass is essentially coming from the modification which an electron will get because of the presence of other entities in the system, because the electron is always subjected to internal forces from the lattices, and the external force such as electric fields in a crystal lattice, the net force may be opposite to the external force. So, therefore, if you calculate the acceleration which happens to an electron, you need to modify the acceleration which happening. So, if you have an electric field, the correspondingly if you have an external force F external divided by ME, you need to modify it with the internal force, and that modification will lead into prediction of a different the characteristic mass or the effective mass for the electron. So, that is why the effective mass concept comes. I just touched upon it because we told about the hole effective mass and the electron effective mass. So, there is much more details to be covered in the electrical conductivity, which is a very complicated and complex phenomenon which is developing in a day to day manner, and that can be dealt in an advanced course. When it comes to the physics of solids, one of the property which needs to be dealt with is the optical properties, which will be dealt in some later stages as part of this course. Thanks for your attention for this session. See you in the next time. Thank you.